question 1. Okay, so don't do question 1. Question 2. Which transformation does not preserve congruence? So if you let's talk about that for a second. Let's make a triangle. Let's assume I had that triangle and I translate it. It's the same triangle, same measurements, same angles, right? So it does preserve congruence. What if I rotated this triangle and now it's like this? Did anything change? No, all the side measurements are the same, all the angles are the same, so did it keep congruence? Same shape, same size? Yes, it did. What if I take this triangle and flip it, right, and reflect it? So if I reflect it over a horizontal line, for example, right, so imagine there was a mirror over here. The new triangle reflected over the line would look like this, right? Like that. And let me bring it down. It would be over here. Well, the original one was over here, looking like this. Right. So again, did it keep the same shape? Did it keep the same size? Yes, it did. But let's look at dilations. So if you have a triangle like this, I decided to dilate it by a factor of 2 or 3 or half, making it smaller or larger. Did it preserve congruence? Did, and now I guess I'll duplicate one more. So imagine I had that, and imagine that was the original, and I dilated by whatever, a half or third. Are these congruent? Are these sides congruent? Is this side congruent to this side? Is this side congruent to this side? And so forth. The answer is no, right? Congruence means the same size. So it would be D. You have two triangles here. This is the original one, right? This is the original triangle. Okay, this is the original triangle. And as you can tell, it got dilated, and it also got, well, hopefully you realize that it got rotated, right? So this triangle went this way. And if you remember your rotations, every single point here of this triangle, all these points on this triangle, right, are exactly rotated 180 degrees, so they all ended up 2 quadrants over or 2 axes over. So we knew there was a rotation and a dilation. Now, what kind of dilation? Well, let's take this side here, right? And that side measures 1, 2, 3, 4, and the corresponding side is this one. So this measures 1, 2, 3, 4, 5, 6, 7, 8. So it went from 8 to a 4, and how does that happen? If you multiply that by half, so we know that the scale factor was a half. So dilation by a scale factor of a half, this one, and then a rotation of 180 degrees. So A is the correct one. Anything that was 1/3, we knew it was garbage, so either was A or B. And B said scale factor, which meant it got smaller, and then translation. This is definitely not a translation, it was a rotation. So that's, you're okay with that. Marcy went from here to here. How does this shape go from here to here? Obviously, it's a translation, right? So you went translation to the left. And then how does 2 become 3? And if you can look at it, obviously it's a reflection, right? A reflection. So notice that this point is over here, this point is over here, that point, and they're all equally distant from the line of reflection, which in this case is the x-axis. So we're looking for anything that says translation. So this is out because there's no translation. This is out. Well, actually, there's a translation here. But it says rotation of 90. Well, no. First it was a translation. So it's a translation left, and there we go, here. And then a reflection over the x-axis, and that's what we talked about. So translation this way, reflection that way. Perfect. which series of transformation shows that figure 1 and 2. So because they're similar, we know that the scale factor used to make it either bigger or smaller is the same for all the sides, and the angles are congruent, right? So it went from here. Well, it doesn't say which way it did go, but it says that it's similar. So if there's similar dilation figure of a scale factor of 4, well, let's see what the dilation was. 1, 2, 3, 4, 5, 6. So this is 6, and this is now 1, 2, 3. So if it went from here to here, that's what do you call the scale factor of dilation was a half, because it went from 6 to 3. So obviously 1/4 is wrong and 1/4. So it got cut by half. So a dilation of figure with a scale factor of a half, and then guess what? It is pointing up right now, and after it's pointing this way. So two things: rotation, dilation, and then a rotation and translation. What the heck? A rotation and then a translation. So it would be this guy right here. Because this triangle got dilated, it got smaller. Let me erase things over here. So the triangle got smaller, right? It got smaller. Then you rotate it this way. So now it looks, it's pointing this way. And then you move it, translate it to the right. Okay. 6 shows the location of triangle LMN. It was rotated 90 degrees. So where are the new coordinates? Well, if it's rotated, and it says clockwise, so let's go clockwise. So that means that this point L is going to be in L. It's going to travel from, so let me put the quadrants 1, 2, 3, 4. So if it's rotation of 90 degrees, L, which is in quadrant 2, is going to go to quadrant 1. M and N, who are currently in quadrant 1, are going to quadrant 4. So I need L to be here in quadrant 1. This works, this works, this works. This one is not, because L is in quadrant 4. Sorry, this one, yeah. L is in quadrant 4. L should be in quadrant 1. Okay, so L is going to go from quadrant 2 to quadrant 1. Now, M and N, they both should be here, and L should be here. That's what's going to happen after a rotation of 90 degrees. So do we have anything that looks like this? Yeah. We have A, and we have B. Now we just got to figure out which of those is correct. So I need some points. So let's look at point M. Point M is 1 and 1. Point M prime, so think about this. Remember what we did in class. We switched, right? These numbers travel, they switched this way, and this guy switched that way. So they're still 1 and 1, right? And it's 1 and 1, but in quadrant 4, who is negative, the second number is negative. So the M prime should be a 1, -1, and this guy here is correct. This guy here, M prime, is incorrect. So the correct answer is A. 7. Triangle ABC is similar, so we know they're similar. So two things we know: their angles are congruent, corresponding angles are congruent, and they're showing it to us, right? And if they're similar, we also know that the sides were multiplied by the same scale factor. So let's find the sides. This 4 centimeters is between this angle that has 2 lines and this angle that has 3 lines. So this side here corresponds to this side here. So what is the length of AC? Oh, they want AC. So let me change a different color. And AC corresponds to this guy right here. Right, so how is this dilation happening? How did this 6 become 14 divided by 4? So this 12 is going to be divided by 4 or times 1 over 4, and that's going to give us 3. And there's our answer. 8. Michael has a triangle congruent to this one that is shown first. Which triangle is Michael? So in order to be congruent, remember that the sides have to measure, are supposed to have the same measurements. Okay, same shape, same measurements. So we can automatically disqualify this guy over here. There's no way this one doesn't even look the same as that one. So same shape, same size. So let's just put some numbers here. So this one measures 1, 2, 3, 4. So this measures 4, and this one measures 1, 2, 3, 4, 5, 6. 4 and 6. Is there any triangle here that measures 4 and 6? 1, 2, 3. So this is out. This one measures 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And there's our 4 and 6. This triangle is congruent to this triangle. This one's too big. 1, 2, 3, 4, 5, 6. That measures 6, and this one measures 1, 2, 3, 4, 5, 6, 7, 8. That's not it. So in order to be congruent, it has to be the same shape and same size. Okay, so that gives us that option. Question 9. Oh God. Let's translate that polygon. 3 units to the right and 4 units down. 1, 2, 3. 1, 2, 3, 4. So there's point Q prime. So R prime is going to be here. V prime is going to be here. U prime is going to be here. And T prime is going to be here. So the exact same shape. Oops. T prime is going to be here. So if I connect everything, get the same. No, I did something wrong. So let me do it again. What did I do wrong here? So that's Q prime. Oh, it's half. Oops, sorry. 1, 2, 3. It's actually in the half here, right here. 3 units to the right and 4 units down. 1, 2, 3, 4. There is Q prime. Apologies. And this one is going to go over here. That's R prime. T prime. This is going to be V prime and U prime. A little better. Okay, so that looks the same. Which statement is true? QV, let me highlight QV. QV is parallel to QR. Absolutely not. V prime U prime, sorry, I read the first one statement incorrectly. Q prime V prime, which is this line right here. Oh boy. Is parallel to Q prime R prime, which is this line. Absolutely not. Right? We can definitely see that's not true. V prime U prime, V prime U prime, which is this line, is parallel to Q prime R prime. Absolutely not. No, no. And then V prime U prime, this line right here again, is parallel to R prime T prime. This line right here. That's true. That's our answer. And just to check the last one. U prime T prime, U prime T prime, which is this line over here, is parallel to Q prime V prime. Absolutely not. So yes, C is the correct answer. Keisha drew a pentagon on a coordinate plane grid. Here's a pentagon. Something with 5 sides. Okay, 1, 2, 3, 4, 5. Then she performed rotation followed by dilation with a scale factor of 5. So she rotated. So let's just assume she rotated this way. And then she scaled up by a factor of 5. So everything got 5 times bigger. Okay? What is true about the two pentagons, about this pentagon and this pentagon? They're similar and congruent. They are similar. Are they congruent? No, because they're not the same. Remember, congruent means that this, for example, which measures, I don't know, 4, would match this one, which measures 4. It can't because it got scaled up, right? You got this 4. If that was a 4, it got multiplied by 5. But that's not true. They are neither congruent nor similar. That's false. They are similar but not congruent. That's the one we want. They're not congruent anymore, right? The sides, they all measure something else. So if that was a 4, this is now a 20. If that was a 3, this is now a 3 times 15, and etc. So the sides grew, all the sides, all the dimensions here grew by a particular factor, in this case 5. So it means that they're similar but not congruent. And the last one, they're congruent but not similar. The last one says, hey, all these sides, this is 4, this is 4. If this was 3, this was 3. And we know that's not true. It's saying that it is, but it's not true. So the only one that's correct is letter C. They're similar, which means the sides were multiplied by the same scale factor, okay, but not congruent. 11. Which transformation applied to figure A to obtain figure B? So how did A become B? Well, obviously, if you do a reflection, for example, if you do a reflection of this over the y-axis, it becomes like that, right? Let me do a better job. It becomes like this. Now, after a reflection, we got to make this triangle go to the right and then down. So definitely a reflection over who? Over the y-axis. So reflection over the y-axis. This one says reflection of y. And then a reflection over the x-axis. No. A rotation. No. A rotation again. No. A reflection over the y-axis and then a translation down. There we go. That's the one we want. Triangle DF, this one that you see, was formed after triangle. The triangle was somewhere, was translated 2 to the right and 2 up. So let's go backwards. So let's go E at point E. So point E from wherever he was traveled 2 to the right and 4 up. So 2 to the right and 4 up. So let's do the reverse of that. So let's go 2 to the left and 4 down. 1, 2, 3, 4. This is where originally the vertex E was. So this triangle was originally somewhere like this, and then it traveled 2 to the right and 4 up. Okay, so we want the exact location. Well, there we go. The exact location is 0 and -6 right here. 13, triangle ABC is dilated by, so there was a triangle. Okay, this got dilated and became this triangle. So we know all the angles inside are the same. So this is 15 degrees, this is 100, so when you're at 15, this is 100, this is 65. So it got dilated, so it got everything got, all the sides got increased by a factor of 2. Which statement is true? Triangle ABC shown here is dilated, so I apologize. This should be much bigger. So this triangle got dilated. Okay, so it got dilated to a bigger triangle, twice as big. So if that was 22, it is now 44. This is now 12, and this is 48. But the angles inside all measure the same. This is 15. It's still 100, and this is 65. So let's read the statements. Triangle A prime, B prime, C prime has measurements of 6, 22, 24. No. Has measurements of 8, 24, 26? No. Has angles measuring 30, 130, and 200? No. And has angle measuring 15, 65, and 100. So the angles stay the same, but the sides double. But none of these sides were correct, so they were wrong. And last one says, hey, the new triangle has the same angles as the original, and that's the one we want. Last one. If you rotate, so there was a rotation. Okay, when it's 180, it doesn't matter if you actually go this way or you go this way. It doesn't really matter. Which statement is true? Angle ACB, this angle right here, ACB. So remember, the middle letter tells you the vertex. So angle ACB is similar, congruent, sorry, to angle XYZ. XZY, this angle right here. Is that true? Okay. No, because this angle here actually is this angle. But that's not true. Angle BAC, we're talking about this angle, is congruent to angle XZY. X, the middle letter Z. Are these two angles the same? Yes, they are. Okay, so notice that this angle here, right, is formed by the shortest side and the medium side here, or maybe the longer side, but it's formed by those two lines, and those two lines correspond to this guy here and this guy here on the second triangle, and those two are the same exact angles. Okay, and you know that those are congruent. Okay, yeah, that's it.